Section 9.5, Hybrid Orbitals. If you remember the idea of an orbital as a college dorm room for two girls that hate each other, you remember it comes from a very complicated math problem that is showing probability of where an electron happens to be at any one time. So if you have this concept of an orbital, which is very useful, it doesn't really beautifully mesh with the idea of the VSEPR model that we just discussed, where you have the electrons pushing the other electrons away and forming very definite shapes. Let me give you an example. If you were to have beryllium is in the second column, and you have 1s, 1s1, 1s2, so that's the first row, and then beryllium is in the second row, 1s or 2s1, 2s2. Well, that orbital is full, and the two p orbitals that are in that period are unoccupied. There's nothing in 2px, nothing in 2py, nothing in 2pz. So those are unoccupied orbitals. The problem is, if you are going to have a compound that you can actually have it in reality, of say beryllium and fluorine. Okay. Now normally that would be an ionic bond, because you have something from the left side of the periodic table and something from the right. But under extremely high temperatures, you can make a molecule of this where you actually have shared bonds and everything. It's not ionic, it's molecular. Well, if I look here and say, my question is, where am I sharing an electron? Because I have a full orbital, so there's no room for another electron in that orbital, and there's no electron to share in this orbital. So if I were to look at this theory as is, I would not be able to explain how that I could have a molecule like this, but you can have it. It exists. So what they have done is they have put together a concept of an orbital that makes sense for both theories. The VSEPR, which is the electrons pushing each other away and making special shapes, makes perfect sense and explains what people see. And the concept of orbitals also explains what people see. So there needs to be a tiny bit of a reconciliation here. So they're going to tweak the idea of orbitals. So we've learned that you have S's, and then the second row you have an S, and then you have 3 P's. Then you would have the 3s subshell, 3p subshell, and 3d subshell. Okay, so then you would have the 4s, 4p, 4d, and 4f. Okay, so you have those concepts. We're going to hybridize them. And a hybrid is where you have two things kind of merged together. So I'll try to explain. They are going to take the S subshell and the P subshell, and they are going to merge the two. So if I have an S subshell and I have 3 P subshells, okay, and I have, say, for beryllium, just the S filled and no P's. Well, what you can do is you can take one of these and transfer it, basically give it a promotion, energize it somehow, so that what you end up with is an S subshell with one electron in it. That way I can share with someone else. I can overlap that and share with another atom that has an empty subshell to share. And then I can do the same with the first P. So now I have two. Remember, you have to have one to share, okay? But you have to have an open space for the other one to share with you. So what they've done is they've taken one and they've made it to the P. Now I have one that's S and one that's P sub X. I still have two normal, okay? The P sub Y and the P sub Z are still normal, but I have now two orbitals that I can share with. What's going to happen is that the s orbital shape, remember this was just kind of a probability shape, was spherical. The probability shape for one of the p orbitals was dumbbell shaped. And so if you hybridize them, you merge them together, you are going to make two. So you have one s and one p, so there's two orbitals. So you're going to have two hybrid orbitals. The same amount of orbitals you start with will be the same amount you end with, but they're going to look a little bit different. They're going to look dumbbell shaped, but they're going to be unevenly dumbbell shaped. They're not going to be as a p orbital is. They're going to be lopsided. And what will happen is this one will have its little guy on towards the inside, and this one here will have its little guy towards the inside, and so they overlap. And here are the two lobes that can be shared. So I've got one electron in it, and I can share two more. So if I have something like beryllium fluoride, well, I can share a fluorine atom with this guy, and I can share a fluorine atom with this guy. I have two lobes to share with. So in order to make what we see, we have to have the right number of orbitals consistent with the compounds that we can actually make. All right, so here is that hybrid, okay, and it's called the SP, and that makes sense, right? I took an S, I took one of the P's, put them together, I made an SP, okay? So I have an SP here, and I have an SP here, okay? And then they're 180 degrees apart, and so when you look at, say, beryllium fluoride, according to the VSEPR model, it is 180 degrees apart. It makes perfect sense, okay? So what's going to happen, here is your first orbital, that's your sp orbital. Here's your second one. But you still have two p orbitals left. You've got a p orbital in the y direction, and you have a p orbital in the z direction. Okay, so if you remember, I had an s and I had three p's. Well, I took two of these, made an sp, okay. So I had an S, I had three empty P's, I took one, elevated it, and made two SP's, and then I have two leftovers P's. So here's the leftover P in the Y direction, here's the leftover P in the Z direction. So here's what it looks like. We no longer have 1S, 2S, and 2P, okay? So here's what we started with. We had 1S, we had 2S, and then we had 2P. What we did is we stole these two, made it a new orbital, called it SP, and then had two leftover 2Ps. Okay, so the hybrid orbital for where you have 180 degrees is called an SP. You're taking one of the S's, one of the P's, stealing it and making an SP, giving one in each, and now I have two rooms that I can have an extra college girl each come in and share. So what's going to happen here is this is your SP from beryllium. CSP, and then you're going to have an overlap region with the F in fluorine, because there is fluorine, remember, is 2p5, so it has an orbital that only has one girl in it, so it has a room to share. So it's going to share with this, and then this overlap is going to be the bond. So the bond for BeF2, if it's a molecule, is going to be a shared region of electrons between the two. Okay, so here's another example. Here is boron. Boron's normal is 2s2, 2p1. Okay, so this is in the third column. It's in the third column, which means that if I look at here, I should only have one room to share. I can hold hands with one thing. I can make one bond. But when you look at what you can make with boron, like we've looked at boron trifluoride before, boron can easily hold hands with three things. Well, how do I do that if I only have one room to share? Well, you can hybridize the orbitals. All right, so now look what we have. We have the S, we've got 1p. So what if I take the other S and promote it to the second room that's open? Then I have one electron in the S, so I can share that. I have one electron in the piece of X, I can share that. I have one in the piece of Y, I can share that. So what'll happen is I need three things, just like this, BF3. I need three rooms that I can share with other atoms. So they're going to steal these three, rename them, and remember, if you have three original orbitals, you're going to have three hybridized orbitals. So I have 1, 2, 3. So I'm going to have 1, 2, 3. And so remember, the first one was called SP, which made sense because I took an S and a P. Well, this one also makes sense. It looks scary, but it's not. It's SP2. Well, what's that mean? It means I took one S and two P's. Okay, so S and P is an SP. SPP is SP2. So I took one S subshell and I took two P subshells, hybridized them, called them SP2 subshells. That leaves one P left over that's not hybridized. And now I have three rooms that I can share that are open for other atoms to share, and those are called bonds. That's how I make a bond. Okay, so remember, the degenerate here means on the same energy level. So I'm going to make three sp2 orbitals. And that makes sense because an s is an orbital and two p's are two orbitals. So together an sp2 would have three orbitals. They're going to be in the same way where you're going to have these lopsided barbells, and they're going to be, there's one, okay, here's the other one, and here's the other one. So they're going to make a triangular planar, which is 120 degrees apart. This is called a triagonal planar. And remember, when you had something like BF3, okay, BF3, that's what you had. You had a triagonal planar on the same plane, 100 degrees. So what's happening, these hybridized orbitals are not in any way clashing with the VSEPR theory anymore. They're overlapping beautifully. They're making the exact same shapes that you predicted when you tied the balloons together. Same idea, okay? All right, so here's that second one. You're going to take an S, you're going to take two P's. You're gonna take two P's. You're gonna take the PX, the PY. Okay, so you're gonna take this one and this one. You're gonna merge them together, and it turns into a lopsided barbell, just like we saw. The lopsided barbells are 120 degrees apart. Okay, so this is 120 degrees here. And then you have the leftover P, the one that we didn't use, that's unhybridized. It's at the 90 degrees, so it's coming straight through. So you think of it as a triagonal planar like that, and then you have it pierce through top to bottom. Imagine these guys on the equator, and then you have one north pole to south pole. That would be the final P. That's what's happening here. So here's 1, 2, 3, 120 degrees apart, and here's the final unhybridized P that are left over. And that's where the electrons sit. So it works beautifully, and then when you make bonds, you're going to make one here, you're going to make one here, you're going to make one here. And then when you look at the molecule, it's going to be 120 degrees apart, just like the other theory suggested. Okay, so here's the next one, carbon. Okay, so carbon is in group 4. So here's what it looks like normally. Okay, we have a 2s, it's full, so I can't share any rooms with that. I should only have to be able to share carbon with 2 bonds. But carbon constantly makes 4 bonds. In fact, the millions of carbon molecules that there are, the majority of them are making 4 bonds. So if the old style of the orbitals doesn't fully answer the question of why do the shapes of these molecules look like they do. Okay, so take these 4, 1, 2, 3, 4, make a hybrid so that I have 4 rooms to share. Okay, so I took one out of the 2s. Okay, now I have a 2s that's a room. I had one already, and I put the other girl in her own room. Now I have 4 rooms to share. So I took the 2s and the 3 2p's, merged them together, and remember I've got 1, 2, 3, 4. So I have 4 orbitals together to start with. So I'm going to have 4 orbitals when I hybridize them, and that's what I'm going to have. I'm going to have an s and 3 p's. So there's 4 rooms. That's why you call it an sp3. To review, if you have 2 where it's 180 degrees apart, it's going to be an sp. You're going to use an s, you're going to use a p, and it's called an sp. If it's 120 degrees on the same plane, you're going to use an s and 2 p orbitals and call it an sp2. And if you're going to make a tetrahedral out of it, okay, then where I have 4, I'm going to use an s and all 3 p subshells and call it an sp3. So carbon will hybridize to sp3 and look like a tetrahedron, and then that's what we actually see with the VSEPR. Remember, if you were to tie 4 balloons together at the knot, you will get a natural tetrahedron. That's just what will happen, because the balloons are pushing the other balloons away, and the electrons are doing the same. They're pushing the other electrons away and making a specific shape, low energy shape as a result. Okay, so we've got the same kind of dumbbell where it's an odd, it's a lopsided dumbbell, and each of the big lobes are heading towards a corner of a tetrahedron. So you have this kind of one going down, one going over, one going back, so the knot's kind of lopsided, but the big lobes are headed towards the corners, and those corners are making a tetrahedron. Okay, so here's another kind of look at carbon. We had 1s2, 2s2, 2p2. That's the electron configuration for carbon. We took one of the girls out of the 2s room, promoted her to the 2p, and now we have 4 rooms that we can have roommates for, and those roommates coming in from other atoms would cause a bond. But we're going to hybridize those 4 rooms and call them sp3 subshells, or sp3 orbitals. And they're going to be the same number that we started with. We start with 1, 2, 3, 4. We end with 1, 2, 3, 4. So the hybridization is going to be called, you still have your inside electrons, no problem, they're the same. But the outer ones, we're going to have 4 of them. Now carbon can hold hands with 4 things. Carbon can make bonds with 4 different elements coming in, or multiple bonds by sharing more than 1 electron. Okay, so here's the same view. You have an S, you have all 3 p's. So you have 4 orbitals to start with. You make a lopsided one just like we saw, an sp3 orbital. You tie them together at the knot, and you end up with a tetrahedron shape. And that's what you see with carbon. It makes tetrahedron shapes all the time. And this is what a bond would be. You're going to have 1 electron living here. So I only have 1 girl in that room. I can have 2 girls in that room. So you're going to overlap, say, one of the hydrogens. It has a girl in that room too. And now the 2 girls are sharing both of these. These rooms are overlapped. So they're sharing the both rooms at the same location, which is kind of cool. That's what a bond is. That's the idea of a bond. Okay. Now, what happens when you break the octet rule? What happens when you go more than 8 electrons in the outer shell? If you remember, we had if you have 2 electron domains, we had a linear. If you had 3, you had a triagonal planar. If you had 4 electron domains, you had a tetrahedral. What happens when you had 5? When you had 5, where it's 1 and 2, and then you had the 3 along the equator and 2 axial ones, that's triagonal bipyramidal, and that's what you're going to see when you share a d orbital as well. So the example I think I gave you before was phosphorus and I don't know, 5-fluorine, so pentafluoride, phosphorus pentafluoride. So you're going to have phosphorus. Phosphorus is in group 5. So I'm going to have 1, 2, 3, 4, 5. So it looks like I should only hold hands with 3 things because I have 3 open P's. But if I promote one of the S's, where am I going to promote it? Okay, all the P's have a room, but remember, phosphorus is in the 3rd shell, the 3rd quantum number. So I have D's there. Remember, I have S's, P's, and D's, but I'm not using any of the D rooms. The D's are there, so I'm going to promote one up, and you're going to end up with a 3s with a room, each room of 3 P's, and 1 room of 3 D's. Well, how many rooms is that? 1, 2, 3, 4, 5. I've got 5 rooms, and so that's what I'm going to have here. And it works the same. We have S and P, we call it an SP. We use an S and 2 P subshells, and we call it an SP2. We use an S and all 3 P subshells, we call it an SP3. So if I use an S, 3 P subshells, and a D, I'm going to call it an SP3D orbital, and and it's going to have 5. It'll be able to hold hands with 5 things because there are 5 rooms, and if I have 5 rooms, I'm going to end up with a triagonal bipyramidal shape as a result, with 3 on the equator and then 2 at the poles. Okay, so here's a better drawing of this. Here's the 3 at the equator, 120 degrees apart, and then 2 axial lobes, one at the north and one at the south. That's 90 degrees there from the top to the middle. So this is 5, and remember, degenerate orbitals means they're the same energy. Okay, so 5 sp3d orbitals, and then the last one would be 6 sp3d2 orbitals. So I'm going to share an S, all 3 P's, and 2 D's, and I'll end up with 6 orbitals, and we're gonna call those sp3d2 orbitals, and they're going to end up making the octahedron. So if I have S, P, 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 and D, that's 5, you're going to end up with a triagonal bipyramidal. If you end up with using 2 of your D subshells, you'll end up with 6, and that's an octahedron. So if you ever have 6 things attaching, so sulfur hexafluoride as an example, you'll end up with an octahedral shape.